All right. Hi, it's Miss Chapman. This is probability, basic probability, and then the next one will be conditional probability. And this is my second time to film this because I totally forgot to record it the first time. So hey, I got a practice run. All right, so on your notes, you're just writing basic probability, and then there's just a couple formulas here that you might want to write down, and feel free to watch, especially this first part at double time. So you should have already learned a little bit about probability, but I don't know what previous classes you had. And we're going to look at a sample space. The general sample space of things is often marked by S because it's a set, and this would be the number of things in the set. So let me just call that the total right now. You should have learned that the probability of picking something from a set, whether it's a t-shirt or a marble, there's always like dice and stuff, is always how many of A there is divided by the total. So that's like the general formula for probability that you learned. So, for example, um, let's add a little bit to that. Let's add a Venn diagram. So here I have a set of, this is my set S. Let's make it a thing. Let's make it shirts. I have 100 shirts and 30 of them are blue and 70 of them are not blue. So A is the set of my blue shirts. Gosh, that's a lot of laundry. So the probability that I, for some reason, blindly choose a shirt at random from my closet would be the probability of A is 30 over 100. Be careful not to write 70 because there's 100 total shirts. And I think with these Venn diagrams, it's so easy that kids make mistakes. So don't be that person. Um, and there are two ways we can write this. Oh, it changed colors. One is 0.3. So that's the way we write it in stats. And then in everyday language, we tend to call that 30%. So people like this 30% chance of rain. They kind of know what that means. But this is the way we write it in IB and statisticians write it. So probabilities are always between 0 and 1. The probability of any event, in this case event A, is always between 0 and 1. 1 is 100%, it's happening, and 0 is 0%, and it usually falls between. Two things to note, which are kind of weird. The probability that I pull a shirt from my closet and it's not a shirt in my closets, the probability of um, a null set is always 0. So the probability that I take a shirt and it's not my shirt is 0 in this case, or it should be. And the probability that I take something from the set S and it's in the set S is 100%. So those seem pretty obvious, but when we plug into formulas, you're going to want to remember that. And it takes practice. Moving on, going fast. Let's go. So we already talked about that. Combined events. So I want to talk about combined events, and I'm going to write the formula. You're going to write it down, even if you don't get it, and then I'll explain it. So if we have combined events, the probability of A union B, looks like a word, the probability of A union B is the probability of A, I feel like that's clear, plus the probability of B, also clear, but we have to subtract probability of A intersection B. Heh, what is that? So let me draw a beautiful Venn diagram. So A is going to be people whose favorite fruit is apples, and B is people's favorite fruit that's bananas. B-A-N-A. Yeah, yeah. Okay, cool. Um, and some people like both of them. So if I wanted to figure out how many people like apples and bananas, I have to be careful because if I added up all the people that like apples, and then I went back and was like, okay, now I'm gonna add up all the people that like bananas. These people got counted twice, and now it looks like there's more people than there actually are. So you have to add up apples, bananas, and then subtract the intersection to find the total, which again seems like super over exaggerated, but when the events get more complicated, it gets more complicated. So let's look at a super Venn diagram here of A and B. I'm going to call it apples and bananas again. People who like apples and bananas. So in our set, 100 people were surveyed, and if they liked apples and bananas, and it looks like 30 people liked apples, be careful not to say 20, and 40 people liked bananas, and then 40 people were like, meh, apples and bananas, the worst. And so let's look at some combined events here. So let me write that out, what we just said. The probability of people liking apples is 30, right? 3 out of 100. The probability that people like bananas is 0.4 out of 100. And the probability that people like apples and bananas, so that overlap is zero point 0.1. Yeah, it's getting dark in here. I should probably turn on a light, but I don't want to pause this video. We'll just make it work. And you don't need to see me anyway, just the writing. So if I want to figure out the probability of people that like apples and bananas without like over counting that middle section, I'm going to add up the probability of A plus the probability of B. Whoa, 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 what? This is awful. Got a little carried away. The probability of B minus that intersection. And again, if I would have just added these two, I would have ended up with 70% plus 40 would have been 110%. There have been too many people here because it's only 100 people. So I have to be careful. And in the end, I get 0.6. So 60% of people like apples or bananas or both. Um, and this is pretty obvious because it adds up to 100 and you could have just subtracted from 40, but we want to know how to get there when the numbers are not so beautiful. Okay, moving on, keeping going, almost done, let's go. So to make it even more complicated or more fun, depending on how you look at it, instead of putting the number of things, we usually actually put the percentage, the probability. So here the total Venn diagram adds up to 1 because it's 100% probability. 40% of people here said nope, hate apples, hate bananas. 30% of people liked apples and 40% of people like bananas. And let's make that even harder and work back. Oh, mutually exclusive first. We talked about mutually exclusive. It just means that a bunch of people like apples, a bunch of people bananas. Nobody likes both of them in this case. So in this case, A intersection B, like where they overlap, is a null set. And I don't like writing equals null set as a math person. That's for like an algebra calculus thing. Ugh. But in stats, we do that. And also the probability of A union B, sorry, intersection, A intersection B, the overlap is also going to be 0% chance of that happening. This is the only case where the probability of A union B would be equal to the probability of A plus the probability of B. Otherwise, no, absolutely no. You always have to subtract the overlap. Okay, example one, given that the probability of A is 0.5, the probability of B is 0.3, and the probability of A union B is 0.6, make a Venn diagram. So we're gonna draw our Venn diagram. You can draw it if you would like and double check. And you kind of just have to think here. So the whole thing's gonna add up to 1, that's clear. Um, I know that the probability of A is 0.5. The only problem there is that all of this is 0.5. So I don't know how much to really put here, and I don't know how much to put here. And by the same token, I know that all of this equals 0.3. I don't know how much is overlapping. So they do give you something that'll help. They say that A union B, like all of A plus all of B, equals 0.6. So on this one, sometimes you have to do it algebraically, but on this one, we can actually just logic our way through. If A and B, all of A and all of B equals 0.6, but A plus B is equal to 5, 6, 8, there's a 0.2 extra. So that's the point that goes in the middle. And now I can think, okay, A is 5, so this must be 3. And do you see that the probability of A is now 50%? There's 0.5. And the probability of B is now 0.3. And so all of that is 6. So that means 40% is neither A nor is it B. So there is our beautiful Venn diagram. You can construct that a bunch of different ways, but now that we have it, we can use it to do more math, just what we wanted. Okay, so if we look at our Venn diagram that's much prettier than the one I made, we can do some math. The probability of A intersection B prime, what does this mean? So the probability of A and where it intersects with B prime. Remember from last class, B prime is everything not in B. So again, all of this and this. So I want to know where they intersect, and they actually only overlap for, oops, I think that I didn't do a very good job of coloring B prime. Gotta do some better. Everything that's not B. Here we go. So they actually only overlap for this 0.3 part. Do you see it? So this would be 0.3. Okay, A union B would be all of A. So all of A plus where it unions with B prime. So A is here, and B prime is everything not in B. And I've got 3, 4, 5, plus I've got 9.9. So union is everything that falls into A and also everything that falls into B prime. We don't have to double count the 0.3, we just have to count it once. But only 10% of the stuff is not recognized by that. Okay, so A, is this the last slide? I think so. A prime um, intersection B. So A prime is everything that's not in A. And I want to intersect that with B. So B is this. And that only overlaps for 0.1. Okay, and can I just write the others? You can check them if you would like, and we're going to practice them in class. Okay, last slide, because I need to make this video faster. The last slide is tables. So we're also going to look at tables tomorrow. I might not say too much about this right now, but we can also, instead of a Venn diagram, make a table. I love a table as well. It's just really easy to see. So for example, if I want the probability of male, that I select someone at random and it's a male, it looks like there's 120 total males out of 200 people. And so I can do math, zero point 0.6. Yeah, 0.6 chance that I just choose a male there. And we can do this for like anything here. I can do the probability of a male intersection smoker. So that's male smoker is 40 over all 200 people, and that is 0.2, yeah, 0.2. So I have a 20% chance of getting a male that's a smoker. So just we can go through and figure those out. Okay, that's it. That's all I have, and we'll practice this in class. Bye.